Welcome to another video. This time, I'll be doing some practice final problems for the class Math 31A at UCLA. This is the first class in the calculus series, I believe. And this practice final is actually a set of 4 exams. It looks like 4 past exams, actually, that was given by a professor at UCLA. And this practice final packet of these 4 exams was given in 2017, so quite recent. I have no idea if this professor still teaches there or who the professor actually is, but regardless, this hopefully could be a good resource for you if you're taking the class there to see possible problems that could be asked and the level of difficulty of some of the problems. Some of them are actually a piece of cake. Some of them require a little more thinking. So with that said, let me add a little disclaimer that I did not write these problems, okay? So if these problems are too hard or too easy, don't blame me, blame the instructor or whoever wrote this exam, actually, these exams. In my past video for Math 31B, people were complaining that the problems were way too easy, which honestly, they were easy, but I'm not the one writing, I'm not the one writing the questions, and there's only so many questions that you can really ask in calculus. You want students to know the same things to succeed in the future classes, the subsequent classes. So it shouldn't be a surprise, honestly, that they keep asking the same things. But anyway, with that said, I'm going to go however far I want on this packet. So there will probably be multiple parts to this, so this will be part 1, all right? So maybe I'll do 1 of the 4 exams, maybe I'll do 2 of the exams. We'll see how I feel. All right, let's begin. Number 1, it asks us to calculate the limits, and it asks to not use L'Hopital's rule. So this one, limit as x approaches 0, 1 over 2x minus 1 over x times x plus 2. So I pre-solved all these problems in the interest of time and to actually have the right answer on the first try. Okay, so, but I'll still explain my thought process as always. Okay, so, and if you have not seen these problems before, I recommend you try them first. You can probably find this problem set online as well if you Google enough. But if you can't find it, you can pause the video, try the problem first, and then come back to see the solution and to see how I work through them. Okay, so with that said, for this, if you plug in 0 right away, you get infinity minus infinity, which is the indeterminate form. Okay, and the technique usually for this is you want to combine the 2 fractions so that you can have infinity over infinity or 0 over 0. And then maybe some things would cancel. We're not allowed to use L'Hopital's rule there here, but usually a lot of things can cancel for these types of problems, okay? So that's what I said. So we're going to combine the 2 fractions. How do we do that? We need a common denominator. So for the first fraction, I multiply by x plus 2 on the top and the bottom. The second fraction, I just multiply by 2 on the top and the bottom, okay? Now they have the same denominator, I can subtract the tops. Okay? 2 minus 2, that's 0, so it's just x on top. All right? The x on the top and the x on the bottom can cancel. Okay? And now I plug in x is 0. So notice I did not drop the limit notation until I plug in x is 0. This is critical. Okay? And you might lose points if you don't have the correct notation. Okay, and the final answer is 1/4 afterward. So again, the technique here is to combine the 2 fractions into 1. Next, this trig limit, limit as t approaches 0, cosine of t minus 1 over sine t. So if you're not allowed L'Hopital's rule, how in the world would you solve this? Well, the trick here is you have to remember your 2 special trig limits. The 2 trig limits are limit as, let's say, x approaches 0, cosine x minus 1 over x, that is 0, and limit as x approaches 0, cosine of, limit as x approaches 0, sine x over x is 1. Those are the 2 limits. So we're going to use that. So we can multiply both the top and bottom by 1 over t. That's fine. So if that's the case, then we can use properties of limits to evaluate the top as one limit, divide by evaluate the bottom as another limit. And these are your 2 special trig limits, as I just said. The bottom should be 1, the top should be 0. So you get 0 over 1, which is 0, and that's your answer. Okay? That's the trick to solve this one without L'Hopital's rule. All right, moving on. Number 2. Okay, this asks us to find f prime of 2 for f of x of this guy. Okay, so go ahead and try this. You should already have a gut feeling that when there's a limit with a variable, you probably want to use fundamental theorem of calculus. And that's the trick to this problem. Fundamental theorem of calculus are the questions with the easiest points, honestly. Okay, this is the trick. How do you do fundamental theorem of calculus? You plug in the upper bound as your limit of integrate, or as your variable of integration. So wherever there's a t, plug in 1 over x. And then you differentiate the upper bound. Okay? Minus, plug in the lower bound, times derivative of the lower bound. So the procedure, once again, is plug in the upper bound, times derivative of the upper bound, minus, plug in the lower bound, times derivative of the lower bound. Okay? In this case, we're going to plug in the upper bound, times derivative of the upper bound, as I just said, minus, plug in the lower bound, times derivative of the lower bound. The derivative of 1 is just 0, so there's no minus term. There's no term to minus, so that's why I didn't write it here, or type it here. So we just have this, okay? And we can simplify. This is just 1 over x cubed. And this derivative is minus 1 over x squared. And that's your answer right here. Okay? You don't need to bother simplifying. Or you could, actually, we're not done yet. We didn't answer the question. So you don't have to simplify, but we need to find f prime of 2. So we plug in x is 2 into here. And that's your answer. The professor didn't even simplify, so just leave it like that. If you have time at the end of the test, maybe go back to simplify if you require it. But honestly, once you get to here, don't waste time to simplify. And it's risky, honestly, to simplify things like this. Okay, so by this point, you should have gotten most of the points, if not all the points. If it's just a matter of simplification, it's just 1 or 2 points. Maybe. So then, or maybe even just half a point. So just skip it, honestly. Okay? Just a test-taking strategy. Okay, find dy dx. Okay, this we need to chain rule. Derivative of secant is secant x tangent x, so secant of inside, tangent of inside, but this is a composite function. We need to chain rule, so the derivative of the inside is 1 over 2 root of the inside of that. Derivative of square root x is 1 over 2 root x. Okay? It's another composite function, so we need to chain rule once again. Derivative of x cubed plus 1 is just 3x squared, and that's your answer. Don't bother simplifying this for sure. Just leave it like this. Most of the time, professors don't ask you to simplify things like this. Okay? So this is just chain rule multiple times. That's the key. This one, we need implicit differentiation. Y is a function of x. So we differentiate the first term, that's 2y, but we're differentiating y, so we need to tack on a dy dx. Okay? Here, we need the product of quotient rule. I guess I use the product rule because this is y to the negative first power. So first, the second derivative of y to the negative 1 is minus y to the minus 2 power. So that's there. But we differentiated y, so we need to tack on dy dx. Plus second, the first derivative of x is 1. We don't tack on a dy dx there because we did not differentiate a y. Okay? Derivative of 1 is just 0. We solve for dy dx, so we move this y to the minus 1 to the other side, and then we factor out a dy dx from these two terms, and then now we divide. And that's your answer right there. Okay? So, this says f of x is absolute value x squared minus 1. We're asked to calculate integral from 0 to 3 f of x dx. So the trick to these absolute value ones is you have to find if the function is negative. If it is, you have to flip it to positive. Because remember, when the function is negative, or below the x-axis, that's negative area. Okay, but we don't want it to be negative because it's absolute value, so we got to flip it to be positive. So when is this function negative in the interval 0 to 3, if it is at all? Well, f of x is negative when x is between negative 1 and 1. You can even kind of visualize how this function looks. It's I did not sketch it, but let me sketch it now. It's a parabola, okay? Originally, it's a parabola. And then it shifted to the, it shifted down by 1, right? So, let me just draw it like this first. If I do x squared minus 1 with that absolute value in red, it'll look something like this. Okay? But we're taking the absolute value. So wherever it's negative, we are going to make it positive. So we're going to essentially flip this portion over here. And then we'll have like this type of curve. Okay, so we'll have this curve here. So that's one way to quickly visualize where it's negative. And it's actually from -1 to 1. Okay, if you know how this graph kind of looks, then it's easy to figure out where it's 0, the switching point. It's when x squared minus 1 is equal to 0, which is x is plus or minus 1. Okay, so that's why it's like that. So therefore, as I said, when integrating from 0 to 1, we're only interested in 0 to 3, so 0 onward. So from 0 to 1, we had to flip it. We had to make the integrand negative, or -1 times the integrand. Okay, so we split the integral from 0 to 1, 1 to 3. Okay, this is just properties of integrals right here. As we just said, from 0 to 1, we got to tack on a negative sign. So it'll be 1 minus x squared. Okay, this is just the original. It's already positive, so we just take it x squared minus 1. Okay, now we just use the power rule on both and fundamental theorem calculus. You can go through the math. It should be 8 minus 2/3. Okay, find the absolute min and max of f on the interval -1/2 to 2. Okay, so how do we do this? Well, technically, we already know how it looks, so we can probably guess. So from 0 to, what was it? 0 minus half to 2. Minus half to 2. Somewhere there. We can probably guess that 2 is the absolute max and 1, sorry, not absolute max. At x equals 2, the absolute max occurs. Okay, that's a big correction because 2 is not the max. Okay, at x equals 2, the absolute max occurs. That's a big difference. The value would be actually the absolute max. Okay, so there's just terminology. Gotta be careful. And the absolute min occurs right here at x equals 1. So we just from knowing the graph or how it looks, we already have an idea. So let's just use the calculus to confirm our guess already. Okay, so sometimes it's helpful to write absolute value functions as a piecewise function. So if we wrote it as f of x is 1 minus x squared for x is between -1 and 1, x squared minus 1 otherwise. So now we differentiate. Okay, so it's not that hard to differentiate a piecewise function. We got to check for differentiability though, but we'll check that in a bit. Differentiate the top, that's just minus 2x. Differentiate the bottom, that's 2x. So the critical points within this interval, -1/2 to 2, are when x equals 0, okay, because f prime is 0 here, and x equals 1, because f prime is undefined here. Okay, remember critical points are when f prime is 0 and also when it's undefined. Okay, why is it undefined here? Okay, so remember, if there's like a sharp turn, it's not differentiable. It's actually a sharp turn here. So again, it's helpful to know how this graph looks. Okay, not differentiable there. And we can tell when x equals 1, because that's like the switching point, right? If x equals 1 on the top branch, that's -2. On the bottom branch is 2. It's clearly not differentiable, because remember, derivative is a limit. So we had to approach it from both sides. One side, it's -2. The other side is 2. So not differentiable, because the left and right hand limits aren't the same. The limit doesn't exist. Okay? Besides the point, that's explaining why it's undefined. But the point here was, these are critical points. We got to keep them. So we don't have to do the first derivative test and find the intervals and all that, because this is asking about absolute maximum. We can directly jump into checking the value of the function at the critical points and at the endpoints. You have to check endpoints as well. Okay, so that's what I did over here. F of -1/2, f of 0, f of 1, and f of 2. Okay, I found the values. The smallest one is the absolute min. Biggest one is the absolute max, which confirmed our guess. Okay, that's how we do this one. Or that's how I would do this one. Next, use the definition of derivative to show that if f of x is this, then f prime is this. So we just use the limit definition. F prime of 3 is limit as h approaches 0, f of 3 plus h minus f of 3 over h. Now we go through the motions. We plug in 3 plus h into x. and 3 into x. Okay, so simplify. Square root of 9 is 3, so more simplification. Now the technique here, if you remember, is to use the conjugate. So when we use the conjugate, the square root goes away and things cancel nicely. Or the main part is the square root goes away. Okay, so if we do that, then we get 2h plus 9 minus 9. Difference of two squares over here. Okay, the bottom is that still. 9 minus 9 is 0, so more simplification. And this h cancels with that h, so more simplification to this line. Okay, now we plug in h is 0. Notice again, I did not drop the limit notation until I plugged in h is 0. Very important. So 2 over 3 plus 3, which is the answer is 1/3, which confirms right there. This is the best type of question because they give you the answer right away. You just got to match it. Show work to match it. If you didn't get 1/3, then you did something wrong right away. Okay. Evaluate integral cosecant cubed x cotangent x dx. So the only technique I think that you know at this point is substitution. What should we substitute? Should we substitute cotangent? Well, the derivative is negative cosecant squared x, but there's still an extra cosecant that's hard to substitute. So what if we substitute cosecant x? Then we would have its derivative is cosecant x cotangent x dx, right? So that seems like it will work. Because we can break off one factor of cosecant from this cubed. Okay, now let's make the substitution. U is cosecant. Du is minus cosecant cotangent, as I said. So this cosecant squared becomes u squared. Cosecant cotangent dx becomes negative du. Okay, now this is just power rule. Minus a third u cubed plus c, and we back substitute. Minus a third cosecant cubed plus c. This one's easy. Okay, next, integral 1 to 2 x cubed square root of x squared minus 1 dx. Okay, so again, the only technique you know here in this class at this point, I think, is substitution. So what should we substitute? Usually, it's a good idea to substitute the inside of composite functions. Okay, so what if we substitute u is x squared minus 1? Du would be 2x dx. Okay, so we can use one of the x's from here, and then it'll be x squared still, which seems like it will work because we can rearrange that definition of u. Okay, so what exactly do I mean? So let's break off one of the x's. Let u be x squared minus 1, again, the inside. Du is 2x dx. We can get x squared as well from this definition of u. X squared is u plus 1. Okay, now we substitute everything, but don't forget this is a definite integral, so we should change the limits of integration. So usually I come to that afterwards, so let's substitute first. So x squared is u plus 1. Square root of x squared minus 1 is square root of u. X dx is du over 2, du with the half out in front. Okay, we got to change the limits, so when x is 1, u is 1 minus 1, which is 0. When x is 2, u is 4 minus 1, which is 3. Okay? Now, from here, we can distribute the square root of u, or it's u to the half power, to both these terms. And then we just use the power rule. And then we evaluate the limits. Okay? No need to simplify, as you can see. So this is the final answer over there. Okay? I know I'm going a little fast here, especially if you're trying to do this live, but hopefully you're pausing the video and coming back to check your answer, okay? We're finding intervals on which this function is increasing and decreasing. So when it talks about increasing, decreasing, we probably want the first derivative to do the first derivative test, okay? First of all, it might be helpful to know the domain of this guy, because I did this problem already. Okay, so what's the domain of this guy? Well, we can't be square rooting a negative number. So that's the big condition. And we can't divide by 0 either. So we just set the inside of this square root greater than 0. It can't be 0 because it will be divided by 0. And it can't be negative because we can't take the square of a negative number. It'll be a complex number then. Okay? So this is the inequality to solve. If I want to have x squared be positive, I just flip all the signs, but I have to flip the inequality sign as well. Just imagine I shifted everything to the other side. Okay? I factor from here. Okay? I don't know why I did it like this, but because I wanted to keep it as greater than 0 to be consistent. But yeah, so I factored from here, but then I also, again, factored -1 for some reason. So you can just maybe even ignore this line. I guess this was just to help me factor it. Okay, but you can ignore that line. If we factor it, we have zeros at 2 and -1. So we kind of do similar to the first derivative test. We just check when this inequality is true. Okay? If we plug in a huge negative number, this would be negative, this would be negative, this would be negative. 3 negatives make a negative. Plug in like 0, that's in between -1 and 2. Negative, negative, positive. 2 negatives make a positive. Plug in a huge positive number. This is negative, this is positive, this is positive. 1 negative, so negative. Okay, so the domain actually of this function f is -1, x is between -1 and 2. This is helpful because we can restrict our analysis to this interval only. Okay? You didn't really have to do this, but it's helpful to know that we can just restrict it to -1 and 2 when we do the first derivative test. Okay? And actually, you might want to do this because otherwise you might have extra intervals in your answer that aren't correct. Okay? But anyway, so now we go through the motions to do the first derivative test. So we're going to differentiate this, which we can change it to a negative exponent and just use a chain rule. Is that what I did? Yeah. So changed it to a negative exponent. First use the power rule and then chain rule to differentiate the inside. Okay? And then I just rewrote it like this because negative exponent, I can move it to the bottom. 3/2 power means it's square roots all to the cubed. Okay? This 2 comes from there. This minus sign, I distributed to that, so it's 2x minus 1. Okay? The critical point is x is half. How do I know that's the only critical point and nothing on the bottom? Well, technically, we do have the critical points, -1 and 2 as well. Okay, but function f is not defined there. So that's why I didn't pick it. Okay, so x is half only. Again, remember, the critical point is when the first derivative is also undefined, but at -1 and 2, that would make the denominator 0, by the way. The function f itself is undefined, so we don't have to check that. That's why I was saying we can restrict our analysis to this closed interval. Okay? So now we do the first derivative test. I even closed the interval exactly like that, right? And with half in between. Now we do the first derivative test. Okay? We'll plug in like 0. The bottom's always positive, by the way, because square rooting something, again, has to be positive. Right? And then we cube it, it's even more positive, right? Okay, so we can only check the top. So we plug in 0, it's clearly negative. We plug in like 1, clearly it's positive. So the interval of increase is from half to 2, not inclusive. And it's decreasing between -1 and half. So again, it was helpful to know the domain because we restricted our analysis. If we didn't, and we didn't have the critical points -1 and 2, then we would have checked intervals over here as well. That wouldn't have made sense. Okay? That's why it was good to check the domain first in this problem. Let me show the answer one more time. Okay? This is the volume problems. Set up but do not evaluate. This is the best. If you just have to set up definite integrals for the volume of the solid obtained by rotating the portion of the first quadrant bounded by y equals 2 minus x, y equals x squared, and the y-axis in the manner stated. So we're going to rotate it about the x-axis first. So this, honestly, if you get the procedure of, at least for me, once I really got down the procedure of drawing my r out and r in, these were a piece of cake, and I never got them wrong, honestly. Okay? Instead of having to guess, oh, is it top minus bottom? In what cases do I do it? In what cases don't? Why is it plus sometimes? Why is it minus sometimes if I'm rotating about some different axis? It was really confusing to memorize different cases. But if I drew the r and r in every time, I never got it wrong because I'm just calculating lengths. Okay, so let me explain. So for regions Okay. At least it seems like in this class you learn the washer method and the shell method. The washer method, if your functions are in terms of x, is convenient when you're rotating about a horizontal axis of rotation, versus the shell method, it's convenient when your functions are in terms of x and you're rotating about a vertical axis of rotation, okay? The x-axis is horizontal, so it's a good idea to use the washer method because the functions are in terms of x, functions of x, not functions of y. If it's functions of y, the washer method would work well for vertical axes of rotation. Okay, I'm sure you've gone over that before, but I just wanted to remind you. So, first of all, you should always sketch the region. 2 minus x, linear line, negative slope, y-intercept of 2. So that's why your transformations help a lot. You can quickly sketch the region. You don't have to draw point by point. Just quickly sketch it. X squared is a parabola. And it says first quadrant, so we're bounded by the x and y axis, okay? So this is the region over here in red. Hopefully you can see it on camera. Alright? We're going to rotate this region about the x-axis. So I always mark the axis of rotation with some arrow. Okay? We're going to draw a radius from the axis of rotation to the further curve. And we call that r out. This linear line is clearly farther from the axis of rotation. And then we're going to draw r in to the closer curve. Okay? The volume is pi integral r out squared minus r in squared. If you remember, we're adding up all those washers, which is like outer circle minus inner circle. Okay? You can watch my other volume videos if you want me to go a little slower there. But this is the formula. Simple formula to know. Remember. Okay? What is our r out? What's the length of r out? The length is just the function 2 minus x. Plug that in. What is r in? It's the length. This is the length. R in, what's the length? It's the function x squared. Okay? And this is with respect to x, so what are limits of integration? Well, x starts from 0 and it stops at 1. How do I know it stopped at 1, by the way? Well, I found the point of intersection. So after we sketched it, I should have first said that we need to find the point of intersection. And how to do that? We just set these two curves equal to each other. 2 minus x is equal to x squared. Moved all these terms to the other side. Factor. So x is 1 or minus 2, but minus 2 is over here, but we're in the first quadrant. So I only took x as 1. So this point is 1, 1. I did technically did not need to know the y coordinate, but it was easy because when x is 1, y is 1, or you plug into that as well. Okay, so our limits of integration, x starts at 0, x stops at 1. Okay, that's the washer method. Now the shell method, again, as I said earlier, is useful if our functions are in terms of x and we're rotating about a vertical axis. Okay, so again, sketch the region and the axis of rotation. Axis of rotation, draw arrows just for you to know where you're rotating about. Okay, and then the formula for shell method is 2 pi RH. Okay, where R is the, sorry, I swapped the R and the H here. This should have been H and this should have been R. Okay. R is let me start with H. H is the height of each shell. And R is the distance from the shell to the axis of rotation. Okay? So this is why it's helpful to sketch a representative H and a representative R. What is the length of H? It's just 2 minus x squared. 2 minus x squared. This is my H. So I flipped the terms. This guy over here is my H. This is my R. What's the length of my R? How do I know it's 3 minus x? So this is where it's hard to remember. Why is it left minus, or right minus left, sorry. Why is it right minus left? Okay, well, okay. So here's where it's useful to know why it's this. So from the y-axis all the way to here, x equals 3, the length is 3. That should be clear. Okay, but it's not a length, this r is not a length of 3. We're short this much over here. How much is it short by? It's short by x. If we keep moving the h, it's short by x. That's why it's 3, the whole thing, minus what's shorted, x. That's how you understand it, and that's how you get it right every time. You just remember its length. Instead of trying to memorize, it's 3 minus x, something minus something. Sometimes it's plus, if it's like over here. Which the minus thing would work, because it'll be like x minus -1, but it's hard to memorize that. So I'm emphasizing, just know that you're just calculating a length and draw the r into h every time. And similarly, draw the r out, r in every time. And when I did it like this, I never got it wrong anymore. Never had to guess anymore. Okay, that's number 8. Okay, this is a typical problem. Prove that the equation, the sky, has at least one solution. How do we show that there's at least one solution? Or at least one value that is... Okay, so first of all, let's define this function like this. That's what solving the equation is, right? To solve it and move it to the other side, then it's equal to 0. So it's the zeros of this function. Okay, so hopefully that's clear first. We're finding the zeros of this function. How do we know that there's at least one zero? What are the theorems that you learn in this class? One of them is the intermediate value theorem. What does that say? That says that if your function is continuous, and let's say there's one negative value and there's one positive value, because one's negative, one's positive, it has to cross 0, because 0 is in between the negative and the positive, right? That's the idea of the intermediate value theorem. I have a short on that, so you can watch that. I made it like a month ago, so you can go watch that to recap that concept if you've forgot about it or if you don't quite get it still. Okay, so to use the intermediate value theorem, the big condition is the function has to be continuous. We know that f is continuous for all real x, actually, on minus infinity to infinity. How do we know that? This portion is a polynomial. Trig functions are also continuous for all real numbers. That's why it's continuous everywhere. I don't think you need to show it, but you for sure need to state that it's continuous. And then if you have time, just say that this is a polynomial, this is a trig function, which you should have learned during the continuity section, that those are continuous for all real numbers. Okay? Now, we got to find a value of x that makes f negative, and a value of x that makes f positive. Okay? So let's plug in easy values of x. Like when x is 0, we get f of 0 is 0 plus 0 minus cosine of 0, which is 1, okay? Which is minus 1. So f of 0 is less than 0, okay? Now we got to find a value of x such that f is positive. So maybe let's plug in pi, okay? If x is pi, we get pi to the 5/3 plus 2 pi minus cosine pi. What's cosine of pi? That is -1, right? So it becomes +1. This is for sure positive. We don't need to know the exact value. Oh, this is the exact value, actually. But we don't need to know that it's, I don't know what it is actually. This is about 6 point something plus 1 plus, I have no idea what this is, but for sure it's positive. So f of pi is positive. Okay, now we can use intermediate value theorem. Therefore, by intermediate value theorem, since we showed the conditions, there is at least one solution in the interval x is between 0 and pi. Okay? You don't have to choose pi. I think the professor in his key used pi over 2. You can show that as well. It will be positive. Okay? Because cosine of pi over 2 is 0, so it's still positive, right? Okay, so that's part A, using intermediate value theorem. Part B says, prove that there's at most one solution. How do we do that? Well, in this class, over a third of it was derivatives. So maybe a good idea is to take a derivative. Okay? So let's differentiate. We would get this over here. Okay? Now, okay, so I'm like looking at how I did it again. So how the professor did it was completely different than how I did it, how I thought to solve this. So I'm going to show you both ways. I feel like my way is enough to show it. But for sure the professor's way, because he wrote it in the key, he or she wrote it in the key, it's good enough there as well. Oh, it's good there for sure, but I feel like my method is more intuitive, actually, and not as complicated. Okay, so let me explain. Method 1. So this is the derivative, okay? We notice that the derivative is actually always positive. How do we know that? Well, when x is between, for all values of x basically, 2 plus sine x, well sine x is between negative 1 and 1. That's the range of it, right? So if it's the smallest value of negative 1, then 2 plus sine x is 1. So 2 plus sine x in general is greater than or equal to 1. It's positive. And this is for sure positive because we're cube rooting something, doesn't matter, we're squaring it right away. We square something, it's always positive. And then times 5/3, that's positive as well. So f prime is positive, actually, on the whole interval, which means f is always increasing. Okay, that should be clear. If f prime is positive, f is increasing. Okay, and it's increasing for all values of x. So if you think about it, if it's always increasing, how can it cross the x-axis multiple times? Impossible. It would have to either flatten, which means f prime is 0, which is not the case, or it would have to decrease and then increase again. Or if there's more than one, then it'll have to for sure decrease at least one time in order to cross again. Okay, so hopefully that's clear now. Since f is always increasing, it can only cross y equals 0 once. No other way, right? Again, as I said, if it were to cross again, f prime would have to be negative. It has to decrease again. Or f prime is 0. It's just flat, and always 0. Okay? Since it's always increasing, therefore there's at most one solution. I feel that's the easiest way to prove it. Okay? So this is what the professor did, method 2. This is what he did, or she did. If there were two solutions, x equals a and x equals b, that means f of a equals f of b, which is equal to 0. Okay, since f is continuous and differentiable on all values of x, the whole interval, if f of a equals f of b, Rawls' theorem, remember that guy, says that there exists a c is between a and b, such that f prime and c equals 0. However, as we just said, f prime is always positive, greater than 0. Therefore, there can only be at most one solution. So you can do this method as well. Okay, but hopefully you see that my method was actually a lot easier. And you didn't have to even use Rawls' theorem if you actually think it through. Okay, that's number 9. Number 10. This is the challenge problem, I think, in this exam, this year's exam. I'm assuming he just took exams from different years or quarters and compiled them into this final, practice final. This says to find the equation of the tangent line to this curve at x equals a for a greater than 0. Okay, this is not the hard part, but this is a variable. So some people get thrown off when it's not numbers. So I don't know why, but it's just a variable. Just do everything else the same. To get equation of the tangent line, we need a slope and a point. The slope is the derivative, and the point, well, we can get the point in a bit. So let's find the slope first, which is, as I said, the derivative. Differentiate this. You need the power rule. Chain rule, derivative of x plus 1 is just 1, so I didn't write that. Okay, y prime of a, so we're evaluating y prime at x equals a, is this guy right here. Okay, that's the slope. The points, we just plug in x equals a here, so a plus 1 to minus 2 power. If I use point slope form, then y minus the y coordinate equals the slope times x minus the x coordinate, which is a. Or right there. Okay? You can write it in slope intercept form too if you want, but point slope form, that's the answer already right there. Okay? This might help in part B though. Okay. Find the value of a greater than 0 such that the area of the triangle formed in the first quadrant by the x-axis, the y-axis, and the tangent line to this at x equal a is a maximum. You do not have to prove a is the maximum. Okay. So what is happening? It might help to sketch it, but you don't really need to. But you can, since it's bounded by the x and y axis, this tangent line should have a negative slope. Okay, but that won't help us. But you can just sketch it to try to help visualize it if you want. But anyway, this is an optimization problem. And the key there, the key to tell it was, area of the triangle is a maximum. We're trying to optimize the area. Okay, so we want a formula for the area to be able to maximize it. We're probably going to need to differentiate it to maximize it. That's the whole point of the optimization section. Okay, so that's what I said here. Goal is to maximize the area, so I want to find a formula for the area, then differentiate it. Okay, so let me actually sketch it. This is the triangle in question over here. Let me shade the area. Okay, so the area of the triangle is half base times height. Right, this is the base, that's the height over there. Okay, so how do we get the base and the height? This point over here, is it not the x-intercept of the line? And over here, to get h, is this point here not the y-intercept of the line? That's the key point here. You have to be able to figure that out. So, as I say, the vertices of the triangle are the origin, the x-intercept origin, x-intercept, and y-intercept. Okay? So, let's find the intercepts. To find the x-intercept, you set y equals 0. So, this is the tangent line, which is this line over here. We set y equals 0, and then we solve for x. So that's what I did over here. So I guess I use point slope form. Y equals 0, and then solved for x. Okay? Be careful with the algebra here. So let me try to go through it. So this is 0 minus that. So this minus sign and this minus sign, I canceled. Okay? I rewrote this as a fraction. Negative exponent, I can move it to the bottom. Same with that. Okay? This, I wrote it like this so that it's kind of clear to see that I can multiply both sides by a plus 1 cubed. If I do that, I'll have an a plus 1 on the left-hand side, and then no a plus 1 cubed anymore on this side. This will cancel directly, so I just have what's on top, which I distributed, 2x minus 2a. So then I solve for x. X is 3a plus 1 over 2. Okay, that's the x-coordinate of my x-intercept. Y-intercept, I set x equals 0. So that's why the slope-intercept form is useful, even though I guess I didn't even use it. So we set x is 0. You solve for y, so I move this term over here, looks like. I factored a plus 1 to the minus 3. So 2a goes there, and then a plus 1 to the first power. So that's there. So then y is 3a plus 1 over a plus 1 cubed. This is the y-coordinate of the y-intercept. Okay, so the area of the triangle is, remember, this is the x-intercept, that's the length b. And this is the y-intercept, which gives us the length h. Okay, if I simplify a bit, I can combine these two, right? Like that. Now I differentiate this, I would need the quotient rule. So a prime is 1/4 is a constant, leave that alone. Bottom, d top, you need a chain rule, be careful. Minus top, d bottom, need a chain rule again, be careful. A chain rule, which is just 1, so you should always be checking for chain rule. Over bottom squared. Okay, we set it equal to 0 to optimize it. Okay, we solve for a now. It looks like a mess, but it's actually not bad. Because we're setting it equal to 0, we can multiply by a lot of things to cancel. So for example, I can multiply 4 on both sides and a plus 1 to the 6th power on both sides to get rid of them. And when you multiply on this side, it's still 0. Okay? So this, I combine 2 is 6, and then I move the 3 up there. Okay? Now, from here, what did I do? I divided by 3 and a plus 1 squared and a plus 1. Why did I do that? Well, I want to get rid of some terms. Okay, so I see that 3 is common to both, so I'm going to divide it. I see that 3a plus 1 squared is common to, 3a plus 1 is common to both. Get that. And a plus 1 squared is common to both, so divide through that. And again, when I divide it on this side, it's still 0, so that's why lots of things disappeared. Now it becomes much easier right here, right? So you just have to be able to see that. Now I distribute the 2 and the minus sign. I solve for a equals 1. As simple as that. Not that simple. But as you can see, it's quite tedious. But conceptually, you can tell, it's not that hard. You just have to be able to realize that you need the intercepts of the tangent line. And those were the lengths of the triangle, which we differentiated and we optimized by setting the derivative equal to 0.